this is a portion of my summer at least. This is where I reverse a portion of Qualcomm's firmware. All right, let's get into it. First thing, I want to give a shout out to JP Blake. He was my boss at my first internship, High Peak Cyber. He helped me a lot. He got me into a lot of the ARM64 mobile stuff and gave me an opportunity to do a lot of hypervisor reversing at the company. So I probably would not be in this position without him. So thank you, JP. So who the hell am I? I'm a research intern at 26 Technologies. I do a lot of mobile security research, Android, Apple, that kind of stuff. I'm also the IG lead for reversing and the co-lead for vulnerability research, along with Ben, who just left, and Dean, who's currently in Dubai, actually. I'm from Fairfax, Virginia, that kind of area, Nova, which is pretty nice if you're in security. And I don't like Linux, and you'll kind of see why I don't like Linux, and I've never really liked Linux for the past 3 years. Okay, so motivation. This is kind of the short list. So I just want to emulate the Qualcomm firmware. I'll talk about what that means. Fuzz it, so try to find some vulnerabilities within it, and then get an EO3 full chain. What that basically means is that I want to unlock the bootloader, and then basically I win. I guess a better version of that basically is, so last year I was talking with a friend. So the way Android, so specifically doing Samsung stuff, right? The way Samsung phones work is really weird because Samsung runs off 2 processors. The first one is Exynos, which is built in-house by Samsung, and Qualcomm, which is built by Qualcomm. These S20s are made by Qualcomm. And my friend has a Qualcomm phone, my roommate does. But the issue is that Qualcomm phones produced in the US, they're not OEM unlocked. So you can't root the phones, essentially. This phone, on the other hand, is, because this phone's like from Hong Kong. So the idea is to essentially get a full chain of 0 days to get all the way up and try to unlock the bootloader and essentially do a manual OEM unlock, which is a pain in the ass, but we'll try to figure it out. And that's a pretty fun process, and we'll try to figure out how that is. And you can make a lot of money off that, like probably like 60. So that's like the kind of all the motivation. So first thing, Samsung versus Qualcomm. So all this phone was done on a Samsung phone, specifically an SMG9860. That's essentially a Hong Kong version of an S20 Plus. The Samsung phone, so Samsung runs mostly off Samsung stuff, but the firmware, like all the pre-boot firmware before the Android operating system itself, is all Qualcomm. Samsung has made their own modifications to this hypervisor that I'm going to show off. To support their own NOC subsystem. Their NOC subsystem is their own security subsystem. However, and this I kind of learned in my job, the Qualcomm firmware is actually kind of ubiquitous across every phone that runs Qualcomm. So you'll find that even if you try to take the firmware off like a OnePlus that also uses Qualcomm, a lot of that firmware is exactly the same. A lot of like the boot firmware is all exactly the same, which is pretty interesting. So specifically, the piece of software that I worked on is the hypervisor. It's not exactly a conventional hypervisor. I'll try to explain. Like a hypervisor, something like VMware, it's very different from that. So I guess before I go into it, I kind of need to give an introduction on hardware-based hypervisors. So hardware-based hypervisors are used to create, essentially run multiple parallel virtual machines. This is essentially what most people here are familiar with. If you've ever used a hypervisor or essentially VMware or VirtualBox, they do a lot of that. So initially, the way things like QEMU work is that they would essentially kind of create like a fake computer in user space. But the issue with that is that's very slow because it requires a lot of resources and a lot of time. If you've ever looked into QEMU source code, you kind of know how that works out. So most architectures saw demand for this, and they came out with their own versions of hardware-based. If you've ever used like a lot of virtualization technologies like VMware, for example, they'll tell you to go into the BIOS and enable stuff like VTX or AMDV. These are hardware virtualization features. With hardware-based virtualization, things became insanely fast because they ran at essentially a higher privilege level than the kernel. So you essentially have this kind of God mode above the kernel, and which is essentially your hypervisor, and that would manage all the kernels. On x86, it's I think unofficially known as ring -1. On ARM, which is what these phones are on, it's known as EL2. Hypervisor does a lot of stuff to enforce separation between the VMs.
stuff like physical memory management, second level address translation. Familiar with those? That's essentially trying to make sure that two VMs can't access each other's memory address spaces. Device management. So let's say you have a GPU pass-through. Your hypervisor will do that and handle your GPU pass-through. Or like, for example, a virtual NIC. And virtual IRQs and FIQs. And that specifically, that kind of ties back. Yeah. So this is really what a hypervisor looks like internally. So you have a hypervisor, run on top of that, run guest OSs. So hypervisor might be something like VMware, Zen, Proxmox, if you use that. And then you have guest OSs on top of that, and on the guest application. I don't know why this application is spanning two guest OSs. That is impossible. Yeah. So hypervisors on Qualcomm are completely different. They really do different things. So the Qualcomm hypervisor is purely something for defense in depth, actually. And specifically goes into a relatively new technology called hypervisor-based security. So essentially, it serves as a layer above the kernel, and essentially helps protect a lot of it. If you're familiar with HVCI on Linux, hypervisor code integrity on Windows, actually not Linux, it's basically hypervisor-based security really ties into that. And HVCI does a lot of the same things that this Qualcomm hypervisor does, which is very nice. So yeah, so the fundamental purpose of this is another layer of defense in depth past the standard user space and kernel space. Because the issue with that is that if you get a kernel exploit, which are not exactly uncommon, well, they're pretty uncommon, but you find them around, you're kind of dead. You're just completely screwed at that point. Because when someone has full kernel access, there's nothing you can do about it. So the hypervisor serves another layer on top of that, which provides more protection. So that's always nice. All right, the interesting stuff. So what did I figure out when I was reversing this piece of software? So there's a lot of subsystems within the actual hypervisor. There's a property subsystem which has a lot of interesting attack surface. The shared memory subsystem, which is essentially a weird heap subsystem. The SMMU subsystem, the HPC subsystem, and memory management subsystem. So let's get into what each of these are. The property subsystem serves as a repository for interesting values. So what that means is essentially a kind of a key store, but not really. So there's two property almost sections. So the first one is dev.cfg. Dev.cfg, interestingly, is a separate ELF file, which is kind of nice because and dev.cfg also contains a lot of the important stuff like certain addresses, certain load addresses, stuff like that. So it does serve as an interesting attack vector. And the hypervisor, the hype, I guess the hype property DAO is within the hypervisor itself. The way the property DAO itself is structured is it's kind of a two-layer tree structure. So the root of your tree is actually the actual section to whether it's dev.cfg or hype. The second layer, dep1, is the actual path almost. So you'll see something like /dev/hype is a path. And dep2 nodes are the actual properties. So for example, one property that I can remember off the top of my head is, so within dev.cfg, you have a path called /dev/hype. And within /dev/hype, you have a property called hypex_codeadder, which is a very important property that if I can manage to modify, would probably make attacking it a lot easier. It's also really obfuscated. In fact, you know what? I might as well show it to you. I call it insanity just because of how stupid it was, like the actual function. This is the disassembly. I have no idea what's going on here. If you recognize this function prototype, please tell me. Like I should not show that on screen. Yeah. So I mean, luckily so luckily the properties, the actual arguments are pretty easy, but it is not an easy. This is a very terrible function. I assume this is probably like some tree traversal. But what is this? Like Qualcomm. What the hell is this? Like this is unreadable. I don't know what this is. Anyway, this is like reading like Vanguard all over again. Okay. Wrong one. Okay, property dial subsystem. Okay, that's pretty cool. Actually, we'll come back to that actually. So the Qualcomm shared memory. So this is essentially a heap-like data structure that is used to store memory between the entire SOC. So the SOC in this case is so a SOC is a system on a chip. A SOC essentially comprises of a series of CPUs. But the reason they're essentially a combination of CPUs, hardware, stuff like that. And they usually have protocols to communicate between all the hardware and keep all the hardware synchronized. A key structure within the Qualcomm SoC is a QCOM SMEM, and that is used to have a lot of shared data structures, a lot of shared data that's really important for the entire SoC to know. It's also used for like inter-process communication. I haven't seen an example of that, but I mean, not inter-processor communication, not inter-process. An example is the RAM partition table. The RAM partition table contains information on usable regions of RAM. So for example, there's a lot of regions of RAM that have been completely blocked out by Qualcomm. They're like, hey, you can't use this region of RAM. So they blocked it out. And the partition table actually contains all that information. Yesterday, I actually managed to dump the partition table, and I'll show an example of how I did that later. Yeah. And there's also a bunch here. I'll probably upload the slides later if I click on this link. This contains all of them. I don't remember how many of these are actually used in the SoC. Yeah. SMMU subsystem. If you're familiar with IOMUs, SMMUs are just IOMUs, but on ARM. The SMMUs are used. I didn't finish that sentence. Okay. Anyway, I made it pretty late last night. So essentially used to protect a lot of devices from hardware-based attacks, from like DMA-based attacks. Familiar with those? There's two device descriptors within the SMU subsystem. One is the GPU, which is essentially a reference to the Adreno GPU on Qualcomm. And there's another one called apps TCU, which I'm new to what that is. I don't know what a TCU is. I think it's transmission control unit, which is for telecom, which is really weird because the telecom should probably be on the baseband. It should not be handled by the AP. That's a different topic entirely. SMU is protected against DMA. That's it. I don't know how useful this is in terms of attack surface, but I have seen like GPU-based attacks before. GPU-based 0 days and end days are pretty common. Not common, like I remember the Mali GPU on ARM had a pretty substantial vulnerability that was weaponized by certain people. Anyway, yeah, the HVC subsystem. This is where it gets fun. This is like the real kind of big stuff. The HVC subsystem is so in ARM. So typically when you're trying to make a call, you make a system. So for example, reads, writes, and maps, anything that needs to access the kernel, you make a system call. And there's a specific instruction for that, SVC, specifically on ARM. On x86, it's syscall, or int, depending on how old you are. So for the hypervisor also has system calls. It's called HVC's hypervisor calls. These hypervisor calls are made by the kernel, and they're used to protect certain data structures. So for example, if you're familiar with kernel exploitation, there is a structure called the CRED structure that is very commonly exploited and is a very common exploit vector. The hypervisor actually protects that. And the only way you can modify that is by making hypervisor calls. They also modify very important structures like PGDs, so page global directories. Yeah. So the structure of a hypervisor call, so you essentially have a series of arguments. It's essentially like a standard function call, except it makes it to the hypervisor instead of like a jump. Each hypervisor call has two parts. So the first argument is always the app code. So the app code is, I believe, essentially what app is trying to access. So there's a series of apps, and each app kind of serves as a broad purpose, serves a single broad purpose. So for example, there's RKP, which is real-time kernel protection. Device management, which is done via HDM, Hypervisor Device Manager. Each of those have their own apps within them. The way you calculate the app code is by ORing this little weird number right here, this OC300C000 with the app number, bitwise OR. This goes in the first argument. The second argument is the actual command ID. That goes in the second. That goes into X1. That command ID tells you, essentially telling it what to do within that app. A few things about command IDs. 0 is always in it. Actually, that's about it. There's nothing really else. Everything else is implementation dependent. Interesting thing, I think I mentioned this on another slide, but I'll just mention it now. This entire HVC subsystem, I believe, is developed by Samsung. This is not Qualcomm, this is Samsung. Yeah, so that is interesting. Anyway, so there's 8 apps. So while reversing, I found 8 apps. Only 4 are actually kind of documented. So undocumented behavior, that's always fun. 0 is app init. At 1 is, so I guess these are the app codes. So 0 command code is app init. That's used for initialization. That is called only within the hypervisor, I believe. It's not actually called within the kernel. App sample, no idea what that is. That's not even a reference in the kernel. There's just a header file for it. Probably for testing. App RKP, that's used for real-time kernel protection. Used for stuff like kernel data protection. Certain kernel data structures can only be done by the hypervisor. So you need app RKP and app HDM, which is for the hypervisor device. This is used to protect a lot of devices like your Wi-Fi adapter, your camera, your USB, your MMC. MMC is used for your for SD cards, yeah, and Bluetooth at a hypervisor level. Don't know what the hell this actually does. I just know it exists. So yeah, there's 4 others. No idea what those are. I might just I don't know. Oh, I don't know. I might just spam it later. Anyway, the final one is the memory management subsystem. This is actually used in conjunction with the HPC subsystem, specifically the RKP one. It's used to protect a lot of hypervisor, a lot of hypervisor specific data, and a lot of hypervisor specific address ranges specifically, and like kernel data protection, kernel data structures as well. You need this subsystem because you're familiar with a physical PFN remapping attack. That's a very esoteric kernel attack. Those help prevent that. So specifically, what that basically means is that you can, within the kernel, you can essentially define certain address ranges. You cannot write to these. But what you can do is you can essentially remap those virtual addresses to so those virtual addresses are mapped to physical addresses. You essentially remap that physical address to another virtual address that's writable. And you just get free access. It's very simple and allows you to do stuff like modifying syscalls. A lot of those read-only structures now become just writable for essentially free. The hypervisor and this specific subsystem make that entire process much more difficult and kind of impossible. Unless you have a 0-day into the hypervisor itself. Yeah. All right, emulation. As I said back in the motivation slide, a key motivation here was emulating it. The reason why I want to emulate it really is because the hypervisor is not the only piece of firmware running on the software. There is a lot of other pieces of software. There's stuff like there's stuff like XBL, which is the extensible bootloader. There is a trust zone. There's a lot more interesting attack surface that is worth investigating. And I'm not going to reverse that all over again. So what I'd rather do is I'd rather just make a working emulator than just chuck it into the emulator and just run it and just actually have some kind of dynamic analysis platform, which is the ultimate goal here. Emulation. The main challenge is that it is damn near impossible to actually emulate stuff because a lot of this stuff is just entirely proprietary. So you really can't emulate it because there's no virtualization backend for it. For example, if you want to do it on QEMU, QEMU does not have any existing implementations for the Qualcomm GPU. You need to write that on your own, and there's other issues like the hypervisor also relies on other pieces of software and memory, stuff like devcfg, stuff like the trust zone. The trust zone simultaneously is also very difficult to emulate. So it's basically a lot of challenges. And really the only way you can do this is essentially emulating devices on I've already emulated a few devices on Khanna, so I've written backends for them. SMEM, I wrote a backend for that. I did some stuff with clocks as well. I also wrote a really tiny trust zone that just provides dummy SMC implementations, which has been pretty nice to have because that, because you kind of need those. Otherwise, they'll kind of just crash. Anyway, building a research phone. This was something that I kind of did in the last week or so, but it's been kind of challenging, actually more like last month. It's kind of been a continuing process. So building a research phone has been really important, and I'll explain why. So what really is a research phone? A research phone, at least in this case, is a phone where you have full kernel access. So you can read, write, execute, and you can retrieve the address of symbols. So what that means, you can essentially run KL sims. So why build a research phone? It is annoying as hell to do static analysis. Don't do static analysis unless you have to. It is terrible. I hate it. I'm tired of looking at Ghidra. I will, yeah, nah, I hate Ghidra. Anyway, so I don't want to look at Ghidra anymore. So essentially what I wanted to do is I wanted to start running stuff on this phone. Because while doing static analysis, I found a lot of important addresses that I need to be able to read from, but I can't because I don't have, because I can't, I physically cannot access those addresses only via user space. And simultaneously, rooting is not enough. So rooting, if you don't know, essentially only gives you super user. So I guess in that case, UID 0. That's not kernel access. Yeah. So essentially, by having kernel access, we can dump any data in physical memory and actually test. We can also test hypervisor calls. I forgot to mention that as well. So you can't make HVCs or the hypervisor calls from user space. You have to make them from kernel space. So you need to be able to access kernel space on the phone. So that's also been really helpful. So now I can actually see what, like, I can run stuff against the hypervisor, which is going to be helpful. Challenges with building a research phone. Samsung is terrible and they're actively violating GPL. So they don't give you your kernel sources. I did email them. They said they were going to give it to me. They did not respond for 3 months. These bastards. If you want to go after them, I recommend it. I implore you to do so. I don't have the time. But if you want to go like chase them down, like the EFF, or I don't even know who like chase their asses down. But please, I don't know. I don't like Samsung. Anyway, so yeah. So they don't provide kernel sources is basically the idea. As a result, kind of most existing methods of kernel access don't really work. So there's a specific rooting technique called kernel sue. That doesn't work because you need to access the kernel sources. Kernel modules also don't work because although kernel modules are in the kernel and the kernel config they're enabled, they actually just completely stuffed out the entire kernel module code. So it doesn't work for shit. So you can't actually insert kernel modules, which kind of sucks. And there is basically no documentation on how to actually patch an Android, which really sucks. So a solution. The solution in this case was essentially build custom tooling. So after significant amount of research, I managed to find a way to patch the kernel. So there's a tool called VM Linux to ELF, which takes our kernel boot image, turns it to an ELF. I built some custom Rust tooling to essentially apply a kernel patch and as well link the kernel patch. Then I just cut off the ELF header and just load it back into the phone. And that worked out pretty well. Now I have full kernel access, and I will show that off in the demo. Anyway, demo time, let's go. Okay, so which one should I do first? Okay, I will do the, okay, that is the, all right, 1 second. That is the phone. So fun little fact about the phone. This is the BTS phone actually, which is absolutely wild. So if you want the BTS phone, by the way, what I recommend you do is get an S20 and then do a firmware update, because apparently the firmware update for the latest firmware update for the S20 is actually the BTS phone, which is crazy. So if you're like Jungkook fan or something, you know, here you go. Just have fun. Yeah, it's not very hard. We're going to look on like XDA forums. If there's many gods on how to update your firmware. Yeah, so that's the BTS phone. Anyway, back to like actual stuff. Yeah, that was definitely an interesting experience seeing the BTS logo come up when I like first did the actual firmware update. That was very scary because this phone took me like a month to get. This is terrible because these phones are from Hong Kong. You can't find them here. So like eBay, like actively searching eBay was a process. Anyway, so I guess the first thing I do want to show is the full kernel access. So what I did is that I created this little program to dump the RAM partition table. Yeah, so I just kind of run this and it dumps the RAM partition table. And we actually know it's the RAM partition table. And we can just run XXD on this. I don't know why Samsung has XXD actively installed on their phones, but apparently they do, which is very nice actually. Very, very happy about that. So if you run XXD, you see this magic right here. And turns out, if you remember this number, if you go to the actual source, like I guess the reversing, where does it get RAM table, isn't it? Get the RAM partition table. it does this magic stuff right here. Compare these two magic values. And these magic values are actually equivalent. So you have 0A. So in terms of, I guess these are all in little endian. So A0, E0, A5, 9B. So in little endian, that'll be 9B, A5, E0, A8. And guess what? That's the exact same value. So that is the random probability table. So apparently my kernel access works. So that is cool. Yeah. So that's kernel access. And you basically have access to everything. So these are all kernel addresses. These are all kernel leaks. So I just leaked the address of kmalloc, leaked the address of this QCOM SM get, and I essentially just ran it against it. So my kernel patch is very funny actually. Yeah, so this is the kernel patch. Yeah. So yeah, it was stupid. Yeah, okay. I did this at like 2 a.m. Yeah. So I mean, it was like it's a running joke between we're like getting like a whole like Fulcrum post, so we're getting a church now. It's great. So the joke was we're making Samsung holy, we're making the kernel holy because Fulcrum is a very introspective guy. He's like basically modern Jesus as far as we're concerned. Anyway, if you don't understand that joke, forget about it. Just don't ask. Anyway, so yeah. So by the way, actually, this was very hard to code because I actually made like, so I actually used these. So I had to constantly switch back and forth to see which one was readed, which one was right, which one was exit, which one was symbol. And I actually had the syscall codes because like I was terrified because like I didn't know because I was like, will my kernel crash? Because I don't even know because like I got 5 things to say. What is this? Is this read? Is this right? I don't even know. So I had to write these like hashtag defines here, just like make sure I didn't like kill my kernel. Anyway, so it's pretty simple code. Also, aux spaded. Thank God aux spaded is a goddamn valid hexadecimal. It is a valid hexadecimal number. I was gonna be like, oh my God, I'm sorry. This is such a beautiful number. I wasted an instruction on this, by the way. By the way, so if you don't know, ARM only has 16. So unlike x86, ARM only has 16-bit immediates. So you can only have so you can only load 16 bits by an immediate. That is different from x86, where you can load any number of bits. You can load a full 64-bit number by a single move. So yeah, I wasted 2 instructions on this. Where did I waste the 2 instructions? Yeah, so I wasted 2 instructions on it. Waste of time, because if you've ever done shell coding, you know your instruction space is very limited. So, but this is way too important. So I did do aux spaded by 2 instructions. Anyway, wasted 4 bytes, but worth it because this is way funnier. Anyway, so that works very well actually, because now I have full kernel access. And this was actually very helpful because now I can throw this into the QEMU emulation and just forget about it. Because essentially what I've been doing thus far is I've essentially been creating dummy data. And I don't know if I'll show the actual QEMU implementation, but I've essentially been creating, like, for example, SNEM is a thing that I had to emulate. I've been creating dummy data with SNEM, which is very bad and very annoying because that dummy data is completely wrong, obviously. Now what I can do is just dump the data off the phone and just upload it to QEMU and boom, I can just forget about it. It'll work 100% of the time, which is very nice. Yeah. If you're interested, I'll probably post some links later on kind of where you can all see this. Okay, that's the first demo, I think. Yeah, that's the first demo. Second demo, emulation. I need to change my emulation. 1 second. 1 second. Where the hell did it go? There it is. Is that it? That's it. I love QEMU so much. Yeah. So that's a lot. It's a very big. Let's run. I have so many tabs open. Oh my God. Okay. It's 4 o'clock. I'm gonna kind of wrap this up here. 1 second. Do you want to type with 2 hands? Okay. Emulation. So what happened? Is it really? That is hilarious. That is hilarious. Okay. What?
You can pin it to your shirt.
Oh, that's crazy. Okay. That is some cool technology. Wait. There we go. That's some awesome technology. I should have thought of that. Okay, Samsung. What is this? All right, there we go. So funny potent debug. Yeah, let's hit it. So, okay, so we're able to emulate quite a bit. A lot of it was this was reversed, so we can actually print the log. There we go. We print all the logs. These are all the hypervisor logs. Very cool. So these are all your version numbers. These are all internal logs, so you can't see these within the kernel. OEM version. I don't know what any of this means, but I guess these are the values they gave it. RAM partition table magic here. This will be solved. Now I have an actual genuine copy of the RAM partition table. As you can see, there's a lot of properties that I couldn't find. Yeah, in the PSCI version. That's emulation. I don't really think there's much to it. Right now, where are we? I don't even know where we are. We are here. So in terms of Gidra, we are somewhere here, which I forget where this is now, but this is somewhere, I believe, in this function. Somewhere here, I think, in like the SMU shift function. Yeah, that's it. Any questions? I don't really have anything else to say. That was a lot. Yeah, what's up?
Before starting research, did you have a patent phone, which was a medium mini 5D prototype that got released in NAC? But now looking down at the YouTube phone, there's no Qualcomm or anything.
Interesting. Okay. I mean, the objective, I mean, I'll definitely look into it. That's definitely a really good suggestion. But I guess the objective is to do this on a live phone. Because my friend's phone is also an S20. So the objective was to do this on like a live S20. Yeah. So I did Magisk first on this, and then I applied the kernel patch. So I have both Magisk and the kernel patch works.
Yeah, I'm just trying to figure out if the thing, the difference after like somebody got root now to like starting systems, and I guess you can't really do that.
That's actually a good. So the way rooting works from a kernel. So Magisk doesn't actually do very much. All Magisk does from a kernel perspective, it just essentially stubs out a lot of the RKP stuff. If you go to the Magisk source code, I wonder if I can find the script actually. Let's call it Magisk boot.sh or something. That is a link.
Yeah.
Got it. There we go. Boot patch, yeah. All the boot patch. Is that
That's what it's happening.
Yeah, so all the boot patch does in terms of the kernel, it just patches this stuff. So it just throws out RKP, removes this thing called defx, and just kind of changes a lot of the assembly, just throws a lot of that out. I essentially kind of replicated this, but just made a slightly more complex kernel patch, if that makes sense. So I guess to really answer your question, what I did is I rooted it via the standard just Magisk method. And then I went back into the kernel binary and just changed it some more, and then reflashed that on back onto the phone.
Maybe part I guess not like that.
What do you mean? You can't. I trust like in terms of how so.
I don't know. I'm just trying to think like utility, I guess. Okay. You said you had a full EL3 thing.
I don't have the objective is a full EL3 chain. So I mean, if I had a full EL3 chain, I would not care about it. Yeah, it wouldn't matter. Yeah, I would love a full EL3 chain if any of you just happen to have that sitting around. Anyway, any other questions? So, go ahead. In an offensive manner, that's a good question. Like from a red team perspective? Just a bit, okay. You just research. Like, it's really vulnerability research. I mean, the objective really is fuzzing it. I guess that's like I mean, if you get a 0 day, like just like kind of chuck it at stuff and you win. Yeah, I do. Yeah, we love to win around here. Anyway, any other questions? What's up? I appreciate it, man.
But I did hear major that I want to research that so actually that and when that has a follow up. So I'm doing it LVR on. Should I be worried?
Should you be worried? No, because this is probably be a full like LP. Yeah. Now then you should probably be worried if you get the chain. But in that case, it's still like a full like LP. So in that case, you're just gonna have to install an app. I mean, if you choose to install like My Sketchy app that does a full EL3 chain, that's about it. Just don't install sketchy apps. Like, I mean, we're gonna come back to a kernel. We do need a kernel exploit, but I do know of some very sketchy Samsung drivers.
Yeah, we felt my point.
Yeah, I've seen some very obscene Samsung stuff around. You can come ask me it later if you're interested. Yeah, what's up?
I don't know. I missed it. We may cover this, but did you use the bundler and so with one?
Not yet.
Okay.
So fuzzing is the objective of because we can't emulate it, we can't really fuzz it. The ideal fuzzer is AFL QEMU or libAFL QEMU. Probably libAFL QEMU, just like granularity control. Yeah. I mean more like AFL plus QEMU. What does it even call it? I don't even know what it's called now. Yeah. But that's gonna be a challenge in and of itself. I was gonna make a slide on that, but that's gonna be a challenge in and of itself because the way AFL plus QEMU works is that it's, I guess specifically ASAN is gonna be hard. So there's an address sanitizer that checks for invalid memory addresses. I guess invalid memory accesses rather, and that's gonna be very hard to emulate. And yeah. But the way I have to look into how AFL QEMU actually. Anyway, I think we're about done here. I think we're out of time. Anyway, very cool.
Clap it up.